All right, so I'm going to go through the types of studies, which is lesson 1.3, part 1, that we did in class on Thursday, September 3rd, and Friday, September 4th, just in case you missed it or want to look back at it. So today we're going to distinguish between observational studies, surveys, and experiments, and then analyze the types of generalizations or conclusions that you can make from them. So you are tasked with determining if listening to classical music improves grades, if it causes an increase in grades. So you decide to interview some of your friends for your study. So firstly, think about what variables could you record in your survey. So for example, you could ask your friends, do you listen to classical music? And that would be a yes or no answer, so that's categorical data. I could ask them, do you listen to classical music while you studied for your last test? And that would also be a yes or no question, so that would be categorical. And then you might ask them, what was your last test grade? Well, that would be a number, so your variable there would be quantitative or numerical. So those are things you could ask, and then from there, you can kind of take your data and look at it and look for patterns to see, do you see a pattern between people who listen to classical music while they studied and what their grade was? So first, let's talk about different forms of studies that we could do. So what could the population be for this study? So our population could be students, but are we talking about all students? Are we talking about at a specific school, maybe in a specific grade level or class? So always think about when you're beginning an experiment or a survey, who is your population? Exactly who are we trying to find out about? So we perform a census when we collect data from every individual in the population. So if we were actually able to take our entire population, whoever that might be, and collect data from every single one of them, we call that a census. The United States attempts to do a census every 10 years where they collect data about every single person who lives in the United States. And it's very difficult for them to do that. If we're unable to complete a census, we can use a sample, which is what we talked about a lot in the last couple of weeks. We perform a sample or a sampling when we collect data from a few individuals in the population. So first we're going to talk about observational studies. So you might prefer to collect data from observations of actual subjects. So just asking your friends the question, do you listen to classical music? What was your grade in your last test? That would be an example of an observational study because we let subjects choose their own treatments. We observe them, see what they made on their tests, and then we record the results. So observational studies do not change the variable being recorded. So we're not like asking our friends to try listening to classical music next time you take a test or next time you're studying. We're just observing what they already do and what they chose to do in their own thing, and then we observed what happened. Observational studies have the advantage that we can record the data and we can determine if there is an association, meaning we can look and see, wow, people who listened to classical music while they studied tended to make higher grades on their tests. We call that an association when we just notice that there's a pattern between one variable and the other. However, that pattern or that association does not imply causation, meaning just because we notice a pattern, people who listen to classical music while they study make higher grades on tests, doesn't mean that classical music causes you to do better on your test. But why not? So let's revisit some of the classical music questions. So what might people who listen to classical music have in common with people who have good grades, besides just the fact that they listen to classical music? So maybe people who listen to classical music tend to be more highly educated. They go to school more, they are in school from a young age, they do extra classes and all that kind of stuff. Right? High education might lead to classical music and good grades. So people who have a lot of education, who take a lot of classes, who study a lot, they might listen to classical music and also get good grades. So that doesn't mean that classical music caused the good grades. Probably the high education caused the good grades. It just also was associated with classical music. So we call that a lurking variable. So that high education, someone who takes a lot of classes and learns a lot, is called a lurking variable because it's the actual cause of both things instead of those two things being connected. So if we really wanted to determine causation, meaning we really wanted to be able to say classical music causes you to get good grades, then we would want to do an experiment. And the way we do an experiment is by randomly assigning subjects to the different treatment groups instead of just letting them choose. So instead of just letting your friends choose to listen to classical music or not, we could randomly assign them by randomly picking some of our friends to be in a group that listens to classical music, and then the other friends that didn't get picked will not listen to classical music. So if we randomly assign our treatment groups, then we're allowed to kind of look at those results, and if there is an association, we can say that one thing causes the other. So sometimes subjects are treated or assigned to a fake treatment, which is called a placebo. So this happens a lot in medical trials. So when we're talking about maybe like a headache pill, we're trying to see, does this new headache pill work better than the old one, or does this new headache pill work at all? So medical treatments oftentimes use a placebo. One group will get like a fake treatment. So even though placebo has no actual impact, subjects might feel better because of something we call the placebo effect, right? So even if you don't know, or even if you're taking a pill that's not a real medical pill, you might still feel better because it's kind of that weird mental, like, oh, I feel so much better because I'm taking something. It's really a strange phenomenon that we notice in experiments. So by randomizing and using placebos when possible, we can control the impact of lurking variables. And the reason that works is because we are randomly assigning our people, our subjects, to different treatment groups. Any of those other lurking variables are going to be nicely kind of just spread out amongst both groups, so they shouldn't have an effect on the overall result. In order to validate the results of an experiment, it is important to replicate the experiment to see if they are repeatable. So really good experiments are not just done once. If we do one experiment with our group of friends and notice that, hey, yeah, if we randomly assign them to listen to classical music, that group tended to do better on their test than the other group. Well, that might work for your friends, or it might have worked that one time and have been a fluke. So in order to really kind of feel good about the results of an experiment, we want to repeat it over and over with different groups of people at different time periods to see if it still works with everyone before we can really truly say classical music causes good grades. The last thing we're going to look at in this lesson is something called a simulation. So simulation is kind of like a virtual experiment. It uses a mathematical model and frequently a computer, a random number generator, to use or to virtually model a situation. We can also do simulations with random number tables. So in our rectangle lab from a few classes ago, I had you guys use Google as your random number generator. And that is always a valid method. You can always use a random number generator to pick random numbers. But in this one, I'm going to show you how we might use a random number table to do the same thing. So random number tables are basically what it sounds like. They're just list tables of random numbers, random digits that were created long, long ago. So before the days of computers and calculators and random number generators everywhere you go, this is how statisticians ran simulations and picked random numbers, is by using a random number table. So I just gave you like a little piece of one on this example today that we'll use, but just know that back in the olden days, there were like books full of these. They were everywhere. So in our example, Maya April Moore is an American professional basketball player for the Minnesota Lynx of the WNBA and is ranked the number 3 player of all time and number 1 on the current best WNBA players. Her 2017 free throw percentage is 86%, or about 86%. We're going to use this line of random numbers to simulate how many free throws she would make in 10 attempts. So in other words, I'm using the numbers to simulate what might actually happen in real life, based on that free throw percentage of 86%. So what I'm going to do is I'm going to look at 2 digits at a time in my random number table. So like the first 2 digits I see are 92. And the reason I'm going to look at 2 digits at a time is because I want to simulate a percentage, right? So we know that 86% of the time she makes the free throw. So I'm going to simulate, let's say that all numbers, all 2-digit numbers from 0, 1, and 86 would represent that she made a free throw, right? So 86% of the time she makes a free throw. So we'll let the numbers 0, 1 through 86, which is 86% of 2-digit numbers, represent that she made a free throw. And then I'm going to be looking at, and all the other times, 87 through 99 and 00 as a 2-digit number will mean that she didn't make the free throw, that she missed it. So if I look at these numbers, these first 2 digits are 92. So 92 in this scenario would mean that she missed it because it's not within that 01 to 86. So she missed it on that first one. The next 2 digits are 21. Well, she made it. That's between 01 and 86. The next 2 digits, and I am going to keep going. I'm not going to go all the way to the 7. I'm going to do the next 2 digits is 07. 07 is within 01 and 86, so she made that one. Next one is 43. I'm sorry, 04. I missed the first 0. So 04 is the next one, so she made that one. 39 is the next one. She made that one. 08 is the next one. She made that one. 62 is the next one. She made another one. 97 is the next one. So 97 is above 86, so she missed that one. 32, she made that one. And then 99 is above that number, so that is a miss. So overall, she made 7 and missed 3. So she made 7 out of 10. So we call that a simulation, where we use this theoretical number 86% to run a kind of pretend model. So instead of actually having Maya April Moore shoot baskets in a basketball stadium, shoot free throws until she gets one in, we're kind of simulating that whole situation by using a number table. Okay, one more real quick trick, or one more example of that. Let's say we wanted to use this row of numbers to determine the sum of 2 rolls in a die. So what I'll do for this one, on a regular die, there are 6 sides. So I'll assume 1 through 6 are results of a die. So when I see the number 6, that means I rolled a 6. When I see the number 1, that means I rolled a 1. So what that means is, in this one, I'm going to have to ignore any zeros that I get, because a die does not have a 0 on it. And I'm also ignoring 7 through 9 because it doesn't have that either. So if I come up to a 0 or a 7, 8, or 9, I'm just going to skip it and move to the next number. So my first roll is a 6. But remember, I'm rolling 2 die, and then I'm finding the sum. I'm adding them together. So my first roll is a 6. 7 doesn't count because there is no 7. My next roll is a 5. So for my first one, 6 plus 5 is 11. So that could be one sum that I get. So moving on, the next roll is a 3, and the next roll is a 2. So that sum is 5. The next one is a 6. 8 doesn't count because I don't have an 8. And the next roll is a 1. So 6 plus 1 is 7. And I could keep doing that. I could keep simulating 2 rolls of a die and adding together those 2 numbers a whole bunch of times and get a pretty good idea of what the sums of 2 rolls of a die could be and what they are most often. So that would be another simulation that I could do. All right, so that is it from today's lesson, or the lesson we did on Thursday, Friday. Hopefully that helped. Have a good day, guys.